Hello and welcome to iStream Ophthalmology, Learning Ophthalmology made simple by Dr. K. Suresh. Today we are going to learn about Sturms Conoid. But before going into the detail of Sturms Conoid, we have to know what is a toric surface. When a surface has equal curvature and focusing power throughout the lens, then we call such a surface as a spherical surface or the lens as a spherical lens. Because light, when it falls on such a surface or such a lens, is focused into a spot of light called a focal point. On the other hand, when the curvature of the surface is unequal, with a maximum curvature in one orientation and a minimum curvature at another angle, it creates what is known as a toric surface. The points of maximum and minimum curvature of such a surface is known as a principal meridian. Toric or astigmatic lenses can further be divided into two types: plano-cylindrical or sphero-cylindrical. Plano-cylindrical lenses have one meridian that has no focusing power, which is the plane surface, and the other meridian is where all the focusing happens, and that is the cylindrical meridian. Whereas when we come to the sphero-cylindrical lenses, it has two meridians and both have focusing properties. So both these surfaces focus light at two different planes. Now let us come to our topic of interest, Sturms Conoid. So what is a Sturms Conoid? A Sturms Conoid is nothing but a configuration of rays that are formed because of refraction of light through a toric surface. So let's see what happens when light falls on a toric surface. As an example, I have taken a toric surface where the horizontal meridian is steeper than the vertical meridian. So as we know, light which is going to fall on the horizontal meridian will converge earlier than the light which is falling on the vertical meridian. So we will study the different patterns of image that is formed along the course of light. So when we take a cross section of this light at point 1, what we notice is the horizontal rays have started converging earlier than the vertical rays, and what we get at this point is a vertically oval image. So let's see what happens at point 2. Here the horizontal rays have fully converged. So because of this, the image we see is a vertical line, and this plane where the horizontal rays have fully converged is known as a first focal plane, as all rays of the horizontal meridian have converged at this plane. Now coming to point 3, here the horizontal rays which had initially converged completely have started to diverge. So what we see is more like a oval image. Now comes the most interesting point, point 4. Here both the horizontal rays are diverging and the vertical rays are converging equally, leading to formation of an almost perfectly circular image. This image is known as the circle of least confusion. The next point, 5, is where the horizontal rays are diverging more, leading to a horizontally oval image. Now coming to point 6, at this place, as you can see, the vertical rays have converged completely and the horizontal rays are diverging, leading to a horizontal line-like image. This point B is known as the second focal plane, where the light rays which have fallen on the second meridian have converged completely. And finally, we come to point 7, where both the horizontal and the vertical lines have started to diverge. So, when we talk about Sturms Conoid, there are a few things which we have to know. First is the first focal plane. This is the point where light from the first meridian has completely converged. Next comes the second focal plane, where the light from the second meridian has converged. And in between these two focal planes lies the circle of least confusion, which is approximately halfway between these two focal planes. And the interval between this focal plane 1 and 2 is known as the interval of Sturm. So let's see the relevance of Sturms Conoid in the eye. We will place the retina along the various points in the Sturms Conoid and see what kind of refractive error we end up with. So to start with, I have placed the retina at the farthest end of the conoid. And what do we see here? The light from the horizontal meridian has converged along the first focal plane, and the light from the vertical meridian has also converged in the second focal plane, and both these focal planes are in front of the retina, and whatever light that is reaching the retina is the diverging rays that are from these two focal planes. So this condition is known as a compound myopic astigmatism, where both the first and the second focal planes are present in front of the retina. Now let's push the retina a little anteriorly. Here, as we can see, the light from the horizontal meridian is still converging in front of the retina, whereas the light from the vertical meridian is converging on the retina. So there is only one focal plane which is present in front of the retina, whereas the other focal plane is present on the retina. Such a condition is known as simple myopic astigmatism, where only one meridian is getting focused in front of the retina. Now let's move our retina a little more anteriorly. What do we see? Now our retina is lying at the point of circle of least confusion. The light which is coming from the horizontal meridian is still converging in front of the retina, whereas the light which is coming from the vertical meridian is converging behind the retina. But both the focal lines or focal planes are lying equidistant from the retina. Now why do we call this point as the circle of least confusion? Because if we go across the conoid, the kind of image we get is the best at the point where the circle of least confusion exists. That is why this is known as the circle of least confusion. So this kind of refractive error that happens when the retina lies at the circle of least confusion is known as mixed astigmatism. Now let's take our retina a little more anteriorly. What happens? Now the retina is lying at the first focal meridian or the first focal plane. Here the light from the horizontal meridian is now converging on the retina, whereas the light coming from the vertical meridian is converging behind the retina. This kind of astigmatism, where one principal meridian is lying on the retina and the other meridian is lying behind the retina, is known as simple hyperopic astigmatism. On taking the retina a little more anteriorly, what we see is both the focal planes are now lying behind the retina. This kind of astigmatism, where both the focal planes lie behind the retina, is known as a compound hyperopic astigmatism. Till now, we learned about what happens to light as it passes through a toric surface and the different types of astigmatism. Now, ideally, depending on the type of astigmatism, appropriate correction is given. So what happens when the appropriate correction is given is the Sturms Conoid is collapsed so that both the anterior focal plane or the first focal plane and the second focal plane are made to lie on the retina. But there are conditions where this appropriate correction cannot be given. During this time, we prescribe what is known as a spherical equivalent. So let's see what is a spherical equivalent. Why do we need this spherical equivalent? See, sometimes some patients cannot tolerate a toric correction, and people who don't want to wear a toric contact lens, and in certain tests like visual field testing where toric lenses are not available, only spherical lenses are available, we make use of this spherical equivalent. Now how do we go about calculating this? It is very simple. The spherical power is taken and half of the cylinder power is added to the spherical power to derive the spherical equivalent. So what does this spherical equivalent do? It basically brings the retina to the site of circle of least confusion so that we can provide a reasonably good image. But the disadvantage of the spherical equivalent is the quality of image is compromised. Let's see how to calculate this spherical equivalent. In this example, the spectacle correction is +1 diopter sphere plus 2 diopter cylinder. So as the formula says, it is sphere plus half of the cylinder. So +1 plus half of 2, which is again +1, which brings us to 2 diopter sphere, which is the spherical equivalent for the above correction. So let's look at another example where the spectacle correction is -2 diopter sphere minus 1 diopter cylinder. So -2 plus half of -1, which is -2 plus -0.5, which gives us -2.5 diopter sphere, which is the spherical equivalent for this power. So this is how we derive the spherical equivalent, and it is very easy.